All right, today we're diving deep. We are going to unlock the most powerful energy source we know of, and it's hidden inside something so small it's almost impossible to imagine, the nucleus of an atom.
So it really all boils down to this one question. How on earth can something so tiny hold so much power? Let's figure this out, because the answer is literally the same principle that powers our sun and every star in the sky.
Our journey starts right here, deep inside the atom's core. Now, this is a place of unbelievable density, where the rules of physics get a little strange. And it's home to just two kinds of particles.
To even start to wrap your head around the nucleus, you have to think on a totally different scale. I mean, it is about 10,000 times smaller than the atom it's inside of. Picture this. If an atom were the size of a giant sports stadium, the nucleus would be a single marble sitting right in the middle. That's what we're talking about here.
So, what's actually packed into this tiny, dense space? Well, you've got protons with their positive charge, and you've got neutrons, which are, neutral. By themselves, they weigh almost exactly the same amount. But, and this is a huge but, when they get together to form a nucleus, something really, really strange happens to their total mass. To understand that strangeness, that little quirk, we've got to turn to the man who basically gave us the master key to the whole thing, Albert Einstein. And there it is, probably the most famous equation in the history of physics. What it tells us is absolutely revolutionary. Energy, or E, equals mass, m, times the speed of light squared, c squared. Now look, this isn't just some boring formula. It's a cosmic rule that says mass and energy are just two forms of the same thing. They're interchangeable. Mass can literally be converted into pure energy, and a whole lot of it. Now, when you're working with stuff this small, you can't use grams or kilograms, right? The numbers would just be ridiculous. So scientists came up with a special unit, the atomic mass unit, or AMU. It's just a standard. It's defined as 1/12 the mass of a single carbon-12 atom. Simple as that.
So, let's put Einstein's big idea to the test. What if we could take just one single atomic mass unit and convert all of that mass, every last bit, into pure energy? How much would we actually get? Well, the answer is kinda staggering.
You get 931 mega electron volts. Okay, I know, that's a unit physicists use. But here's all you need to know. For a single atomic particle, that is a colossal amount of energy. This is the whole secret we've been looking for. Even the absolute tiniest speck of mass is a massive reserve of locked-up energy. And that idea right there leads us straight to the central paradox of the nucleus. It's a mystery that, once you solve it, reveals the source of all nuclear power. I mean, this is just bizarre, right? Think about it. If you take a proton and a neutron and you weigh them separately, and then you weigh a nucleus made from that exact same proton and neutron, the nucleus actually weighs less. It's like some of the mass just vanished. So where in the world did it go? Physicists actually have a name for this missing mass. They call it the mass defect. It's simply the difference between what the nucleus should weigh based on the particles inside it and what it actually weighs.
So where did that missing mass go? It didn't just disappear. It was converted into pure energy, exactly like E equals mc squared said it would. And that energy is what we call binding energy. You can think of it as the cosmic glue that holds the entire nucleus together, overpowering the natural force of the protons that are trying to push each other apart. It's the energy price you have to pay to build a stable atom. Okay, so if binding energy is the glue holding a nucleus together, then messing with that energy is how we release it. See, every atom in the universe kind of wants to become more stable, and it does that by increasing its binding energy. And it turns out atoms have two main ways to get more stable. Really heavy nuclei, like uranium, they can split apart, and really, really light nuclei, like hydrogen, can slam together. In both cases, splitting or combining, that move towards a more stable state releases enormous amounts of that binding energy. So the first path is nuclear fission. This is what happens when you split a heavy, unstable nucleus, uranium is the classic example, into two smaller, more stable nuclei. That difference in stability, that change in binding energy, gets released as pure power. The second path is nuclear fusion, and it's pretty much the exact opposite. Here, you take two very light nuclei and you slam them together under incredible heat and pressure. They merge to form a single, heavier, and much more stable nucleus. And again, that increase in binding energy gets released as a tremendous burst of power.
So there you have it, two different paths to the exact same goal, releasing atomic energy. Fission splits things apart, fusion brings them together. Both are unbelievably powerful, but they work in completely different ways. Let's break it down. Fission, you're splitting a heavy nucleus, and it needs a trigger, like hitting it with a neutron. Fusion combines light nuclei, but it needs insane conditions. We're talking temperatures of millions of degrees. And while fission gives us a ton of energy, fusion, pound for pound, or I guess particle for particle, releases even more. And here's why any of this matters. These aren't just ideas in a physics textbook. We have actually harnessed fission. It's what powers our nuclear plants, our cities, our submarines. And fusion? Well, that's the process that's lighting up our sun and every single star across the universe. So that kind of brings us to our final thought here. We've mastered one side of this nuclear coin to power our world today. The other side, fusion, powers the entire cosmos. The question that's going to define our future is, can we finally bring the power of the stars down here to Earth?